Hello. I really want to go over the different stresses and failure modes in beams. So at chapter 14 they introduce bending, but leading up to 14 we've had axial, which is just stress is equal to force over area. And I would really consider this as like a tensile failure check. So like this kind of loading. Okay, and then we've got shear, which was, now that we've introduced shear diagrams, shear force over area. And so now we're going to have bending, which to me is MC over I. Okay, and so for a little diagram. So this is if like there's a force down and a force up. Bending. It's going to look like this. Okay. So here's your beam. So if you're bending your beam, you're going to have generally compressive force. Here, this diagram right here. You're bending up right now. The moment's coming up. You're going to have compressive force on the top, tensile force on the bottom. So generally, I've got a toothpick to fail. Generally, if you think about where is this going to fail, ooh, that was a really good example of longitudinal shear, which we'll get to in a second. It's going to fail on the tensile side. Yeah, like that. So it fails first on the tension side. I'm not sure if you can even see this. I can't focus it. It's fine. But on the top here, it's these fibers aren't broken yet, and on the bottom here, these fibers snapped. So on the top, the fibers are still whole, and on the bottom, they've started to break. So on the top here, it was in compression, and those fibers didn't break. So when you think about metal as well, it's going to crack on the tensile side, whichever that may be, depending on your bending condition. And when I think about bending stress, I usually think about this formula. And I is it's just a formula depending on the geometry. And normally you have rectangles and circles, but if you were to have like an I-beam, it would be a much more complicated I. So I look at a table for I. So basically you've got your moment diagram, and so you figure out what your maximum moment is, and then you consider your geometry. I is base times height over 12, base times height cubed for a rectangle. So this would be like with a 2x4. So if you had a 2x4, and let's say you had some kind of loading condition, And so your moment experienced by this would be, based on the length of this. So you figure out what your moment is. And so if it's bending like that, then, and your 2x4 is oriented like this, then this is going to be your height, and this is going to be your base. Okay, so, I base height cubed over 12 for a nominal 2x4 would be, sorry, it's base 1.5, 3.5 cubed over 12. And then, yeah. So let's just pull some numbers. Let's say we got the same moment as them. Which that looks pretty high. Let's see, they're doing a 4x10 cross section, spanning 10 feet, uniform load of 450. Yeah, we should just do their example. So they got 3.5 by 9.25. I guess that's the nominal for a 4x10. So then the I for a cubed. So I got 320.8. 230, sorry. That's going to be inch to the fourth, because this is inches, inch cubed. Okay, and then they just gave us a moment, so like, oh, they didn't, they actually used a, is it simply supported? Must be. So their loading is 450 pounds per foot. And it's 10 feet across. So we've got 4,500 total pounds. So each reaction is going to be 2,250. So then our moment at, I guess our maximum moment for simply supported should be in the center. So right here. Shear is ramping from 225 down to 0 at 5 across 5. So really my moment's the sum of this area. So this is feet and pounds. So my moment is equal to 1/2 225 times 5. Okay, that explains it, because it's half of that. I'm off by a factor of 10. calculator. Okay. Whew. Okay. And this is pound-feet. Okay, and then this is in inches. So now I've got my moment. I've got my area. So I don't need my area, sorry. It's I of a 4x10. And it was 230.8 inch. Then I've got my moment. And it's going to be 625 feet. So I want to turn it into inches. So it's 12 times that. Six, 7, 500 pound inch. Okay. So now C is half. It's the distance from your neutral axis up to your top, or to your maximum point of tension. So for me, I just remember it's half of a rectangle, half the height. So MC over I. So in this case it was 9.25. So C is just going to be half of 9.25. So bending 7, 500. 9.25 over 2. 230.8 inch. And so that's MC over I. And this would give you the maximum tension in the beam. And compression. So the tensile stress, bending stress, 13.5 to 6. So let's do 1350 pound per inch squared. Should come out inch squared. Let's check that out. This is pound inch. This is an inch here. So I've got a pound on top, 2 inches on top, 4 inches on bottom. So I should cancel 2 of these with 2 of those. So yeah. Now, with that information, you would consult these tables of material properties for wood. Where was it? I thought it was back here. Steel pipes. Timber, A6A. Here. This is giving me area. Oh, it actually has a table for inertia. Let's see if we can find 4x10 231. So you wouldn't have to calculate I if you looked here. I wanted the stress though, the bending stress. Okay, yeah, here it is. Yeah, let's do ultimate. It doesn't even give tension. Let's do compression then. So the ultimate compression is 5. So we checked bending. But here it's saying shear is a lot lower. Okay, so let's go into that. Okay. So now, once you're bending, especially wood, you'll have a shear force that's along the grain. And so there's a tendency for the grain here to slip under bending. So there's something called longitudinal shear that you have to check once you're bending. So I had a perfect example earlier with that toothpick, and it's going to be 1.5 V over A. So shear longitudinal, because we're bending, for a rectangular cross section is 1.5 V over A. And then the next page it says for a circular cross section, three-fourths V over A. Okay. So you've got axial stress, shear stress, bending. Shear because of bending is a little higher. Okay, so if you're fine from normal shear, like when you plot your diagram, and you're working with the wood, you'll probably have to multiply by 1.5 to then go consult the chart. And then after this, there's a bunch of chapters talking about deflection and material properties. And I kind of want to skip all of that and just go over buckling. Okay. Buckling doesn't have a super simple formula, but it's something you really need to consider. So like, if you're pushing in compression, it's going to buckle instead of squish, linearly. So in the real world, when you have these like long, skinny members, they're not going to fail due to compression. They're going to fail due to buckling because it'll just suddenly give out. And so this example is it's called first mode buckling. But if you step on a can, like an aluminum can, and it has a bunch of folds all the way down, that's going to be a higher mode. So I kind of want to just introduce the idea. I don't need you to be able to mathematically prove what will buckle and how to fix it. Is it at 19? Yeah, columns. So there's a lot going on in here, and so most of my classes, this was at the very end. Um, so like if you have a 2x4 that's going to fail due to compression, it'll probably buckle. Okay. And it'll probably be the first mode. And so here's a load, elastic modulus, I, and then the length. And they're just saying, they're not even considering stress in the beam. They're just saying this is the load at which it's going to fail. So I think if I was going to highlight anything, that would be it. And from there you could have different factors, and it gets super engineering-like. I'll just write it down for the benefit of this note. So the load critical pi squared elastic modulus of the material, pi squared elastic modulus of the material, that I factor that I just talked about. So for like a rectangle, it's bh cubed over 12. Divided by L squared, the length of the column. And so your beam could fail at any one or any number of these, actually just one, or a combination.